the evening for me, so that's funny. And my clock just tells me it's 1/2 the hour. I expect people to still trickle in, but you know, I'm German and we have a packed agenda, so this is what's happening. Welcome to the Internet Congestion Control Research Group session at IETF 122. I'm Reese Enghart. I'm a co-chair of ICCRG, and all of our chairs, unfortunately, have to be remote this meeting, but we have Eric Kinnear joining us as delegate in the room, just in case we need somebody in the room. Thank you, Eric. All right, so this is a hybrid meeting, as you can see. If you are in the room, please make sure you scan the QR code in the room or use the link from the meeting agenda to join with a full client or a thinner client or whatever on your phone. This session is being recorded and the recording will be uploaded on YouTube. If you want to speak, please use the Meet Echo tooling to raise your hand. And if you're remote, please mute your audio and video unless it's your time to speak. And also if you're remote, please use headphones. If you're on site, please also use the tooling to raise your hand and then line up at the mic. And please remember to state your full name before speaking. Before we get started, a couple of policy reminders. The IRTF follows the IETF's intellectual property rights disclosure rules. This means that if you are aware that an IRTF contribution that we are discussing is covered by patents or patent applications that are owned by you or controlled by you or your sponsor, you must disclose this fact, or you must choose to not participate in the discussion. And you must file your disclosure within days or within weeks and not months. See the referenced RFCs and website for more information. As I mentioned, this session is recorded, and if you speak at a microphone or on camera, you consent to appearing in such recordings. The recordings will be made public, and the IRTF has a privacy policy regarding how we handle your personal information. You can find more details on the slides and behind the links. We also require respectful conduct from all participants or attendees. If you have any questions, any concerns, please talk to us chairs. For example, you can email us, and there is also an ombuds team, which you can reach through the contact information linked out on this slide. So please read our code of conduct and our anti-harassment procedures. And I mean that seriously. They are important and they are central to making sure we can do the best work possible within this group and in general. So the IRTF is not the IETF, and this is an IRTF session. The IRTF focuses on longer-term research issues, and the IETF focuses on shorter-term issues of engineering and standards making. One way to put it is the IRTF's goal is understanding, the IETF's goal is a product. See also the linked RFC 7418. The IRTF does publish documents at times which are informational or experimental in nature. And the goal here is to promote development or research collaboration and teamwork. ICCRG actually has 2 active research group documents right now. Both are related to LEDBAT, a lower than best effort congestion controller. ICCRG has worked on both of these documents for a while, so we're preceding the newly formed CCWG. As these documents were already adopted in ICCRG, the chairs felt it was most appropriate to just keep them in ICCRG and move towards publication here. And to that end, towards publication, our LEDBAT is almost done. Yay. And LEDBAT++ is not as far along, but it has a new revision, and we will briefly talk about it in a couple of minutes. And here's our agenda for today. As I said, it is very packed, and right. And we will need a note taker. Do we have anybody who's willing to take notes for us, please?
Nobody?
Come on, please, folks. We need a note taker. and I can't see the room well. So if you can just drop a line in the chat. Eric, I can see you.
I can take it.
Thank you, Simone. Okay, so I'm just gonna have one slide on the hackathon because we don't have a lot of time, and then we're gonna proceed to our amazing lineup of presentations. So at the hackathon, there was a congestion control testing table, and we don't have time to go into detail now, but huge thanks to Mohit Tahiliani and his team of students. They gave a wonderful presentation at the hackathon results presentation session yesterday. So I linked out their recording and results slide from this slide. And I understand TSVWG on Wednesday will have some of their FQPi results as well. Okay, so that is, I think, all I had for chair slides. And now let me see if we have anything that needs to be done here. And I'm gonna switch over. Okay, so our first agenda item is also going to be me because I'm presenting on behalf of the authors of LEDBED++. LEDBED++ has gotten a new revision, 02, and our 01 was back in 2020. Then we did unfortunately not see an update for a couple of years, and I think the authors may just not have had the cycles to work on the draft, but LEDBED++ is actually deployed and it's actually widely used. So we believe it would be useful to publish LEDBED++ as an RFC. And Marcelo Baniulo, who's also a co-author of our LEDBED, the receiver-driven LEDBED draft, volunteered to help ICCRG bring this document over the finish line by serving as editor and by incorporating some of the changes, the feedback that we're getting. So the current chairs took a look at LEDBED++ and provided some feedback, and then Marcelo made those changes. Thank you. So that includes a new section on experiment considerations, security considerations section update, and some text in the introduction. So with that, LEDBED++ has already been adopted a long time ago, and it has gotten a recent update and review. We believe that LEDBED++ is sufficiently mature to proceed towards a research group last call. So that means everybody now got reminded that this draft exists, and now everybody will get another chance to look at this document and to share their thoughts on the mailing list. Does anybody have any thoughts on LEDBED++ that they want to bring to the microphone right now? Okay. I don't see a hand. So let me share our slides. Okay. We have, I believe, Michael first up. Yes. Okay, Michael, you have control over the slides, and I'm going to start the timer.
Okay, hello, do people hear me?
Yes.
All right. Okay, this is an update on the draft on pacing and transport protocols. This document gives guidance to implementers by discussing general considerations and consequences and giving an overview of how others do it. So it explains how some implementations work that already exist. We had a version 0 and 1, as it is when you have version 2. It's 0. 0 already started with a description of Linux TCP that was based upon a Google Docs document that I had written that some people started to cite and look at. One update that happened now is that we replaced that with a citable reference. So this is now actually a paper. Quick PBR and open source implementations were discussed based on Google's quiche and Meta's MVFST. Then there was version 1, which added Vidi Goel and Michael Tüxen as co-authors, who started adding text on pacing in Apple OSs and FreeBSD, which both is making a beginning, but a little bit high level, and the plan is to extend this text a little bit. So in version 2, the news is there was a bit of discussion on the mailing list and also some private emails, which led us to extend the discussion text that we have. Primarily, that's based on list feedback from Ingemar Johansson and Eduard Vasilenko. There is some new text on Q dynamics. There is some slight brief mention of AQM interactions. And some text on RTT calculation that came from Ingemar. He cautioned that when pacing algorithms would use the SYN-SYNAC handshake, they might actually see a larger RTT for having taken a longer break, which has effects at the link layer. So there is a bit of discussion on that. It's generally written. We have a plan to extend that also with a bit of an elaboration on how this plays out differently when it's happening on the client or on the server side. There's a little bit of text on mini bursts and their trade-off. For example, Eduard has been suggesting that it's good to point out that a burst that may seem tiny at a high-speed link is actually becoming a larger burst nearer the client. If we had that example of sending, for example, 50 kilobyte, which on a 100 gigabit per second link is 4.1 microseconds in terms of time. So that may seem like a completely negligible burst, but when that traverses a 15 megabit per second link, then it becomes 27.3 milliseconds, which is significant. So seemingly tiny bursts are worth splitting up if it is doable. When they reach the receiver, they traverse lower capacity links, they may become significant. On the other side, there are benefits from aggregating data for the sake of, for example, link layer aggregation. Whereas mechanisms that we heard about in the panel discussion, was it 1 or 2 IETFs ago? We don't take a side in the whole thing, we just document the trade-offs a little bit. That's something we added. The main next steps that we have planned are to add more detail on the Apple OSs and FreeBSD. Also, there were some inputs regarding application control. There is, for example, Scream, which has a certain way of doing it in relation to video, because that's really what it was made for. And there is a paper on a mechanism called SEMI in SIGCOMM 2023 explaining how Netflix does it, which is to do with limiting the rate by, as the application would allow it, again, for the sake of video. So there may be some considerations there that we plan to also include in the text. Are there more general consequences of pacing to consider? Well, this is still an open issue, as an issue in GitHub. Oh, by the way, that's also a news that GitHub, no, sorry, that was a different draft. Anyway, so we have the GitHub URL at the end, I think, and you can see the open issues there. There is some material in papers. There's a very old paper that cautioned on all various problems with pacing that may not actually be real problems, but we will have to go through them and check them. This is a pretty old paper, actually. A question that I would like to ask is whether this could be ready for adoption, if the group would be interested in adopting it. After all, at IETF 120 and 121 and at the mailing list, we did see significant interest in this document. Yeah, that's it from my side. And here's the link to the GitHub.
Okay, we have one person in the queue. I believe, Cortez, you're in the room.
I think I read through the draft. One more potential addition to the consideration section is many streaming.
I'm sorry, Almost nothing.
Hello.
Yeah, me neither.
Can you try
Do it
again?
first.
Maybe speak louder.
Hello. Can you hear me?
Yeah. Yeah. Now I hear you better.
Okay. You can hear me. So I read through the draft. One potential
Oh, now.
potential addition to the consideration section would be how certain real-time streaming and even kind of VOD video streaming applications rely on burstiness to determine max bandwidth of the link. So having the transport now doing pacing can throw those algorithms off if they are kind of relying on things being sent in a burst. Like as you have a trade-off section, so this is again like something to list as a trade-off.
Well, I think this is something for the consideration section on how applications interact with the pacing logic. So that's the kind of text that we wanted to talk about anyway. So if you consider, for example, the SAMI paper that has a way of doing that, but you need to incorporate the application layer with the transport layer to do this correctly, yes.
Thank you.
Hi, Lars Eggert, Mozilla. So on the question that the chair has asked, I think this is ready for adoption. I think the content is useful. We've been discussing it for a long time. Hi, Costin. If this was an IETF document, I would sort of maybe quibble a little bit whether everything that's in there is really like in scope for an IETF document, but it's not, right? And so it's completely fine for a research group to have this sort of content, and let's please do this. Thank you.
Question?
Yes. Thank you, Michael, for this work on pacing. There's one thing that worries me about pacing is that we are seeing in various applications some kind of downward drift of the pacing rate when the application is not application is limited. And what's happening is that because we have pacing, we don't push so hard during the peaks because the peaks get smoothed. And then basically what happens is that the application says, oh, I don't have enough bandwidth. So they redo the video compression, use more compression, whatever. And we see this downward drift to the point where the application almost stops in some applications.
Yeah. That's really the same problem as the first speaker had. If you don't incorporate knowledge about the fact that you are pacing in the way the application is measuring the throughput, then you get that. That's what they also wrote in the SAMI paper. It does happen exactly as you say.
It'd be worth having a couple of words about that in the draft.
Yes, yeah, and in the part that we're going to write on the application transport layer interaction.
Yeah,
we'll say that.
and because it's very easy to. I mean, I've seen that trap happen many times already. Okay, that's all.
Okay. Oh, I'm sorry. I think Michael was trying to share
No,
slides.
No, sorry as well.
Okay, no worries. So that all sounds great, and I see Lucas said in the chat, I can't think of a reason you wouldn't adopt this, so I'll take that as additional input. Right, sounds great. Michael, you're satisfied?
Yeah, absolutely.
Okay, great.
awake.
Then let's move on to our next
Okay.
speakers. Let's see. So we got Zeki. I will pass you slides control, and please unmute your microphone and video if you choose to.
Okay, it works. Okay. So
Yeah, you're a little quiet.
can you hear me?
Yes.
Okay. So I can start. Okay. Sure.
You can be a little bit louder, maybe.
Okay, maybe I need to turn on. Okay, here. Closer. Okay. So good morning, everyone. This is Zhe from Tsinghua University, and today I'm very happy to introduce our recent work on the congestion control in the emerging LEO satellite network. So let's begin with the short backgrounds. So over the past few decades, we have witnessed the rapid evolution of the internet. However, yet to this date, it is still challenging to provide the low latency, high-speed internet access for remote area, oceanic, mountainous regions. So how can we change this state? Fortunately, the recent LEO satellite networks are making something different to connect the unconnected. We have witnessed that many leading companies such as SpaceX and OneWeb are actively deploying their constellations to provide low latency and high-speed satellite internet connectivity to remote areas. So take Starlink as an example. By February this year, it has launched more than 8,000 broadband satellites and serving for more than 5 million subscribers around the world. So this figure plots the architecture of today's LEO satellite network. Here, LEO means low Earth orbit, and we can also call it LSN for just a short for LEO satellite networks. So it is a global network with LEO satellites and distributed ground stations and terminals. So let's look at this figure. Broadband satellites are constantly moving at the space and provides internet access for terrestrial users. So data packets originate from user's device are forwarded to a dedicated satellite terminal, then goes up to satellites, goes down to a certain ground station and to a gateway, or we can say it's point of the presence, and finally to the terrestrial internet. So different from many existing terrestrial networks, one characteristic is that a portion of the network nodes are constantly moving. So this can change, can involve many new challenges because this, we call it LEO mobility. It can cause the network instabilities such as the frequent path changes, radio rescheduling, and capacity fluctuations. So here we plot three figures that shows the real world performance of the, for example, Starlink. Here, these results are measured from two terminals from our research partners located at Madrid and New Jersey. So here we run iPerf and use the ping tool to measure the maximal throughput, the RTT, and the loss rate from the satellite terminal to a nearby cloud server. So here we can observe that the link capacity can drastically fluctuate, for example, between 10 to 65 Mbps. Also, we can observe the RTT can drastically change, and with a few packet bursts, more than 100 and even 200 milliseconds. Also, we can find that the end-to-end flow can experience unpredictable and bursty packet loss, even though the data rate is very low. So to understand how this LEO mobility involve new challenges on existing congestion control algorithms, we call it CCAs, we performed a measurement study to inspect the performance of existing CCAs based on the real satellite network. Our experiment study includes two paths. The first path is conducted by the real world measurements. So here we use iPerf and TCP dump to measure the performance obtained between a satellite terminal and a nearby cloud server. And here the terminal is located in Madrid. Okay, so we can use iPerf and run different Linux TCP congestion control and measure their performance. But one thing we should note that the real satellite network is very uncontrolled, and the network performance can change drastically over time. So this experiment sometimes is uncontrolled and hard to reproduce. So as our second step, We also build a lab environments. So we use the TCP dump to capture the PCAP files, and we implement a tool to record and replay them in our lab environments to build a trace-driven emulated network environments. So this environment is fully controlled and reproducible, so we can repeat different experiments under the same network conditions. So this is the performance results from our real world statistics. This is a big picture. We want to say that because the real Leo network conditions can drastically change. So here we run each congestion control algorithm for more than 30 tests, and each test lasts for more than 2 minutes to obtain the statistic results. So here we plot the average throughputs and average the RTT and 95 percentile RTT results in this picture. Let's first look at the loss-based congestion control and the delay-based congestion control. Here, we just select some very representative, well-known CCAs as Reno, Cubic, Vegas, and COPA. COPA is a recent congestion control from the research community. So here we can observe that the loss-based congestion control and the delay-based congestion control work here. Their delay can be their RTT can be very low, but unfortunately, we found that they fail to fully utilize the available link utilization, and they can only achieve about 5 to 10 Mbps in our test bed. Then we also check the performance of the recent BBR, and we know that it is a model-based congestion control. The good news is that BBR perform much better in terms of the throughput than Cubic or Vegas than existing the loss-based and delay-based congestion control. So they work here. We also check the different versions of the BBR. So the first observation is that BBR version 1, the first version, can achieve the highest throughput in our test bed, but also it involves a very much higher RTT than these existing algorithms. And the version 3, BBR v3, the throughput is slightly decreased as compared to the version 1, but it also caused much lower delay, and it achieves similar delay as compared to the Cubic and the Vegas. In addition, we also examined the performance of some learning-based congestion control. We know that the research community recently just proposed to use machine learning technology to regulate the sending rate for internet congestion control. One representative work is called PCC virus. This is a very amazing work. They use just to treat the network as a black box and regulate the sending rate based on the observed loss, RTT increase, and something like that. So here we found that the result is for learning-based congestion control, it is very hard to converge to optimal points because we found the Leo networks, the change in Leo networks is too unpredictable and they drastically change. So it is very hard for learning-based solutions to converge to the optimal working points. Okay, after checking the real-world results, so we want to know the performance details and the detailed behavior of different congestion control. So we just record and replay the real Leo satellite network in our lab environments, and we perform a trace-driven emulation to examine the detailed performance. So we first look at the loss-based congestion control. Here is the results for Cubic and Reno. Like we found that here the ENV rate means the real link capacity, the environment rates. This is a blue line. So we can find that because there are many random loss, Leo network link is a lossy link. So Cubic and Reno could overreact to this non-congestion packet loss. That means we can observe many loss that's just due to the Leo mobility, not because congestion. So they just overreact to the loss and reduce their sending rate. So they suffer from very poor throughputs. Then let's look at the delay-based congestion control. We all know that the underlying principle for delay-based congestion control is that this congestion control use the queuing delay estimation as the signal to prop congestion. So here we just take COPA as an example. So this is how COPA estimates the queuing delay. It maintains two windows, a short window and a long window. So here the RTT mean is the minimum RTT observed over a long window. And here the RTT standing is the minimum RTT observed over a short window. So if in Leo network, because the real RTT can drastically goes up and down, so we always can find that COPA can underestimate the real RTT and the mean RTT, and as a result, it always overestimates the queuing delay. So because the queuing delay is overestimated, so the COPA will reduce its sending rate because it thinks, oh, the network is congested. So as a result, we can find that the real sending rate of COPA is much lower than the actual link capacity. That is, we saw that the link is not fully utilized. So again, let's look at the model-based congestion control, BBR. So we all know that BBR is a model-based congestion control, and it uses two important estimators. One is for bandwidth estimation, and the other one is for minimum RTT estimation. Both of these estimators use the samples observed over a past window for estimation. So to estimate the bandwidth, it uses a maximal filter, but because the real bandwidth can fluctuate, when the bandwidth just suddenly goes down, it will overestimate the available bandwidth. Similarly, if the RTT suddenly goes up, it will underestimate the mean RTT. So as a result, we can find that BBR V1 usually overshoots the available band link and cause very much higher queuing delay than the BBR V3. And especially when the available bandwidth suddenly goes down, we can observe a very high loss rate in BBR V1. So in the latest version, the BBR V3, it makes an important modification is that it adds a loss threshold. So if the observed loss rate is much higher than this threshold, then V3 will reduce its sending rate. It has some threshold and some control in its latest logic. So because Leo satellite network is a lossy link, so BBR V3 just think, oh, this packet loss are caused by congestion, so it will reduce its sending rate. So this figure shows how BBR V3 re-aggregates its sending rate in Leo satellite network. We can observe that it also cannot fully utilize the link, but the good news is that its latency is much lower than the first version of BBR. Okay, so here we found that the fundamental challenge made by Leo satellite network is that the massive non-congestion network variations break the fundamental models and assumptions of existing CCAs. So how can we mitigate this issue? So we think that one potential way is to identify and filter out these Leo-induced non-congestion variations. So we ask the question, is there an effective indicator to help endpoints to distinguish non-congestion related performance changes? Okay, here we just found that while the satellites are constantly moving, satellite operators typically can manage and schedule this mobility. For example, here is this picture shows the SpaceX official documents, and we can find that the SpaceX has a global reconfigurator to schedule their connections on 15-second intervals. Similarly, it also has a local reconfigurator, which happens on the terminal. For example, when the weather is very poor and signal strength is very poor, or the terminal is obstructed, so it will suddenly switch to another satellite. And this information can be obtained by a gRPC service in the Starlink terminal. So we can use this method to extract when a reconfiguration happens. And then we plot this figure. figure shows the strong relationship between a LEO reconfiguration and the network variations. So here we plot a global reconfiguration, local reconfiguration, and the variation of the maximal link capacity and RTT. So we have two observations. The first one is the capacity and RTT can be filtered as a step function divided by a sequence of reconfigurations. And when a reconfiguration happens, the maximal capacity and the mean RTT may change suddenly if it goes up or down. But inside a reconfiguration step, the capacity and RTT changes are relatively mild and smooth. So based on this insight, we just have some preliminary ideas on how to mitigate and make the congestion control more resilient to these LEO-induced network variations. So here we call that we can use this reconfiguration information to optimize the network estimations in LEO satellite network. So the key insight is that many existing CCAs use time window-based estimator to probe the network conditions. So when a reconfiguration occurs, CCAs on the sender can clear the historical data, which is independent within the current reconfiguration interval. So following this key idea, we made two modifications on existing CCAs, just like COPA and VBR. So what we did is we only use RTT samples after a recent reconfiguration for this RTT mean estimation and RTT standing estimation in COPA. And we also clear those bandwidth and RTT samples before reconfiguration if it occurs recently. So here are some of our very preliminary results. By this motivation, we can improve about 74 throughput for COPA, and the latency is just almost the same. And for the first version of BVR, we also made some modifications, and we can find that the average RTT can be reduced by about 30%. Okay, so our work just want to say that because the new characteristics of the LEO satellites, the community, we think we need to pay attention to mind these misleading effects of the LEO mobility. And let's conclude the work is that the unique of mobility, LEO mobility cause drastic end-to-end variations and involve new challenges. And just here we perform a study and to reveal our insights and as our future work. We hope our findings can help for the CCA research and future standards. And also here we put some very awesome, useful reference measurement work here. And we hope if you have interest, we hope you can just look at this work. And thank you very much. This is my talk. Okay, thank you. Any questions are more than welcome.
Great. And it looks like we already have Jeff in the queue and then a couple more.
Thanks, Jeff Houston. Interesting work. Your bandwidth and delay estimations appear to be unique to you and not shared by many other folk who are also working on Starlink systems.
Oh.
Most retail providers around the world, and I've certainly measured in Europe, America, and Australia, get a raw bandwidth through these systems these days of between 230 and 300 megabits per second. And the RTT levels are actually a lot lower, between say about 25 up to 40 milliseconds. You're reporting much, much higher RTT numbers and much, much lower bandwidths, which is kind of unique to you and not to everyone else. My second observation is that you've actually got two components in the capacity signals you're trying to measure. The first is the dynamics of low Earth orbiting satellites and the whole issue of the way Starlink does adaptive code modulation to pack as many bits into each frame as it possibly can. And because you're constantly changing the modulation of every single frame, you get this large variation of round trip times. And that's what you're addressing. But there is a second issue as well, that you've got conventional multiple use contention going on. and that the BBR streams or the TCP streams you're looking at are competing with other streams on common bearers. And that actually requires a more conventional approach, assuming you can figure out what's due to satellite dynamics and what's actually due to contention and sharing. And that's where I see this work is kind of, the starting input is really weird. It seems to be intrinsic to you, not to everyone else. But secondly, in trying to sort of figure out how to address that, you're looking at the satellite dynamics, the signal dynamics be used by Starlink, but not looking at the contention issues, which are also impressed upon the same signal.
Thank you very much for your question. You have some very amazing question. I just try to answer. So the first question is that we just found that for the satellite networks have some very similar strategies, just like today's Wi-Fi and cellular network, that they are very likely to build an independent queue for different terminals. So maybe the contention should occur, but we are not sure whether it occurs at the uplink or the downlink. And again, for these results, you said that the result is lower or higher, right? So our result shown here is mainly focused on the uplink. So the uplink is, we can record this figure. Yeah, so you can see that the throughput, this is the uplink throughput. So it can drastically change between about 10 to 65 Mbps. So, okay. So for the next question, yes, I think the contention is also very important issue. But as the first step, we just want to explore the situation where the satellite link is a bottleneck, maybe not in other portion of the entire end-to-end path.
Okay, thank you for that. We do have about 7 people in the queue. Zilli is next. Please try to keep your questions or comments brief.
Oh, sure, yeah. So very nice presentation. My question is just still trying to wondering why BBRV1 does not work here. Because I assume the RTT, like why the RTT plays in a role is because it uplimits the congestion window of BBR, right? But I'm wondering, can you just remove the congestion window limit in the BBR of the 2 BDP and just rely on the rate estimations? Would that be helpful to adjust to these changing scenarios?
Okay, so I can turn to these slides. I think you are asking questions on these slides, right?
Or like this RTT underestimation will not be critical anymore if you remove the congestion window limit in the BBRV1.
Okay, so because it's just use a maximum filter, so when
yes, just use the rate.
Sorry?
Yes.
Like this, because if you just use a maximum filter, so it will overestimate the bandwidth, but sometimes it will also underestimate the mean RTT. So as a result, the BDP of the entire estimation, sometimes it will be overestimated, sometimes it will be underestimated. So it is a not accurate estimation on the BDP.
But like BBRV1 does not need a BDP, right? It's rate based. You only need to know the rate.
So yes. So as a result, it will sending about 2. I think if I'm 2 BDP in flight data, right?
Yeah. So just get rid of that limit, and I think will that helpful?
The result is the queuing delay is very high.
Okay.
Okay. Next.
Gurtej from Apple. Thanks for sharing this. One first question about the learning-based rate controllers, the machine learning-based rate controllers. You said they don't perform. We've asked, or you said they don't perform very well. Is it just because they've not been trained with data set collected on LEOs, and we feel like they can be trained on this data and they'll perform better once that's done?
It's a good question. So I'm happy to say that these drivers do not require any pre-training. So we do not use the specific data to train this model. We are not sure whether a well-trained model for neural network will work and how good it will perform. But I think that is something we can do in the future.
Yeah, and one quick follow-up. You said you created a lab environment?
Okay.
Is this like based on NS3 or some standards-based model that we can test our congestion control algorithms on? Like, are you able to share the environment?
Oh, we are not using the NS3. If you want to share the environment, maybe we can discuss with our partners because the data we collected from our research partners.
Okay.
We can
Thank you.
discuss offline.
Great, thank you. Next, Cory.
Hi, Gori Fairhurst. Thank you for bringing real data here. It's always nice to see real measurements. Yeah, and they all vary depending on what you measure in a system that's very complex. I wondered if you'd done any measurements using more than one flow at the same time, because you talk about loss due to the satellite, but you don't talk about loss due to actual congestion. Have you looked at that as well?
Oh, I know. Yeah, actually, as the first step, we maybe this preliminary work mainly focus on the loss due to the link. But as our future work, we will definitely research on the more complex scenario, mixing the satellite lossy and other congestion cost loss.
Yeah. Okay, be interesting to see that results as well.
Okay, thank you.
Stuart Chersher from Apple. In the interest of time, I'll just make some quick comments. Thank you for presenting this work. One suggestion I have, you use the term performance many, many times. And I think from the context, you're using that as a synonym for throughput.
Okay.
And I'm not particularly picking on you because we all do this. It's been ingrained in us for years. Let's try not to treat throughput as the only thing that matters, and performance equals throughput, and more throughput is always better. To me, performance encompasses induced queuing delay, induced packet loss through to sending too fast, because there's more than just throughput that we care about. That's my first point.
Thank you for suggestion. We are clarifying.
It's just a question of, if you mean throughput, use the word throughput, right?
Yeah.
Let's try, and this is for everybody in the room. Let's just try to stop using performance as if that's a synonym for throughput. On slide 15, you talked about massive non-congestion network variations. I didn't quite understand that. Because to me, when we use the word congestion in this community, in this research group, congestion means sending data faster than the network can carry it.
Yeah.
And you have to fix that by stop doing that. Stop sending data faster than the network capacity. So what are non-congestion network variations?
Okay. Just here, we just want to express, for example, the network is congested and the router begins to drop the packets, and the packet loss is caused by congestion. And because the satellites are moving and the links are changed, so we also can observe packet loss. So this packet loss is not caused by queuing or other things, other congestion factors. So this is what we want to present here.
Okay, so that leads nicely into my last point, which is you talked about non-congestion losses, and you made an assertion, which may be true, but you didn't present any evidence, that links are just lossy. They just lose packets for no reason. We don't know why. Cosmic ray something. That's just the way the internet is. It loses data all the time, and that's why you shouldn't slow down when there's packet loss. It's really interesting to investigate that, because I've seen in many contexts, give one quick example, people always tell me that microwave ovens make Wi-Fi lose packets because Wi-Fi is lossy. We even have IETF work groups talking about lossy links. It's in the name of the working group, as if that is just something we accept, that some links are just bad quality. They're just bad engineering. They're not well designed. They don't have the right forward error correction or link error acknowledgement. They're just bad links, and we have to deal with that. And you can look at this superficially. If you're sending 600 megabits of data through a Wi-Fi access point, and then you hold your phone by the microwave and turn it on, if you look in Wireshark, you will see, there's lots of packet loss. Packets go into the access point and they're not received. but it's not because weird stuff just made the packets disappear. Wi-Fi has extremely good link layer recovery.
Yeah.
The problem with
Link
holding
layer
your phone by the microwave is that the transmission rate dropped from 600 megabits to 60 megabits. And as long as you're putting 600 megabits in and only getting 60 out, obviously you're losing 90% of the packets. But that's not Wi-Fi layer loss. That is congestion loss until the sender sees what's happening and slows down. So when you talk about losses, I really suggest, and with a Wi-Fi access point, you can only get that information by instrumenting the access point. The fact that a packet goes in and doesn't come out doesn't mean it was interference on the wireless. It might just mean that the rates were out of alignment, and until the sender slows down, the excess is going to be lost. So I'll move on because I know we're short of time.
Thank you, for your suggestion.
Yeah, thank you, Stuart. Sounds like a great conversation over lunch. I know, Eric.
Eric Kinnear, Apple. Yeah, just really briefly, first, thank you for bringing this. I think this is really interesting data, and it's really nice to see. The one thing that I thought was extra interesting here is when you're talking about, hey, can we look at certain signals that we use to say, throw out what we thought we knew and readjust to the new world? And I know that's a thing that's very common in this kind of scenario, but it'd be interesting to spend a little bit of time digging into where else we see that happening. One of the ones that we've looked at a little bit is, say you're on a cellular network and you're switching between different radio technologies. If I switch from 4G to 5G, or I switch to millimeter wave and away, I potentially have drastically different capabilities of the network.
Sure.
And so I don't even know that that kind of reset is satellite network specific. That's something that we might want to generalize more broadly to additional areas.
Yeah, thank you for a good suggestion. One thing I think that's the thing that is constantly and frequently. We are not always switch my 4G, 5G like that. Okay, we can. If I'm running off.
Yeah, I'm just going to already share the next slide, but I hope everybody can have great discussions following this. Okay, there we go. T-Bot, you have control of the slides now, and I'll set you a timer.
Thank you very much. So I'm Thibaut Cholez from the University of Lorraine. This is a joint work with Orange, the French national ISP, and I will be talking about improving cloud gaming traffic quality of service. And we evaluated a class-based queuing policy and the L4S architecture. So I will try to go quite fast on the problem statement because I'm pretty sure you are familiar with this. The use case we studied is cloud gaming. This must not be mistaken with online games. In cloud gaming, we have the game fully remotely executed on a remote server, and the player just has a light client that will send the player's inputs, and the server will provide a multimedia stream in return, and we have this feedback loop that must be fast enough for the game to be responsive. We have several cloud gaming platforms like NVIDIA GeForce Now, Amazon Luna, Microsoft, Sony, they have their own, and Google Stadia has been shut down, but it was working quite well for a couple of years. So there are many advantages that are seen in cloud gaming. First, player has instant access to many games. It doesn't need to have expensive hardware on the client side, and we can think of mutualizing hardware on the server side. But the constraints are regarding the network access that must be quite performant. We will see by how much later to have a good quality of experience. And there are discussions about the carbon footprint that can be worse, but it really depends on how the player is using the service. So over the past few years, there has been a steady growth of cloud gaming, and there is a chance that it will become a significant part of internet traffic share in the upcoming years, depending on what will be the console manufacturer strategy for the next generation. So what does cloud gaming traffic look like? Nowadays, all modern platforms, they rely on RTP, so the real-time protocol. The traffic is has a high throughput because we are talking about high resolution video streams ranging from Full HD to 4K at a high number of frames per second, most of the time 60 frames per second. And also we have a lower compression rate because we use real-time encoding on discrete GPUs. We don't have time to send lost packets, so platforms, they rely on forward error correction instead. And they use proprietary or at least undocumented congestion control algorithm. So what are the why is cloud gaming traffic difficult to transport for networks? Because it requires at the same time a high bandwidth around 30 megabits per second, a low and stable latency around like we have only a few dozen of milliseconds to have the feedback loop, and no loss. So it is really subject to the buffer bloat phenomenon. I'm pretty sure you are quite familiar with this. So the issue here is that we have this queuing latency that can degrade the quality of experience of players. And also we have a poor cohabitation between loss-based CCA that will fill the buffer at the bottleneck and delay-based CCA that will like lower their bitrate, their throughput before loss-based CCA, and they will lose the bandwidth. And the issue here is that traditional AQM, they tend to apply a single policy, which is irrespective of the difference in the application objective being either delay oriented or throughput oriented. So the consequences we want to avoid here is the high queuing latency in case of congestion, and also the poor cohabitation between loss-based and latency-based CCA. So the solution we want to evaluate here are solutions that use separate queues. And we use HTB, hierarchical token bucket queuing discipline, and L4S, the low latency, low loss, and scalable throughput. For HTB, it's based on traffic classes, and we have shown in a previous paper that cloud gaming traffic has its own signatures that make it possible to identify it in real time in the network, to prioritize it and dedicate a short queue for it, if possible. And on the other side, L4S, it relies on a specific architecture and on the ECN field of the IP header to have early notification of the network in case of congestion. But on the other side, the application must comply with a few requirements regarding its congestion control algorithm. So with the research question, the first one is rather rhetorical. Is cloud gaming traffic affected by buffer bloat? And then we want to evaluate how much dual queue solutions can improve cloud gaming quality of service. So for that, we had to do our own cloud gaming platform because the previous one was still relied on TCP and was not realistic anymore. So I won't go into details. You have the link on GitHub, and you have more information in the paper regarding our cloud gaming platform, which is open source, of course. And the CCA we use for our cloud gaming platform is Scream, developed by Ericsson. It's a CCA for RTP that is compliant with L4S. That's the main feature we are looking for. And Scream, it is like a proxy that will drive the RTP video flow on the server side according to the signals it measures on the network. And it will tell the cloud gaming server which bitrate to follow and request iframe when needed if there are loss events. And we did a first assessment of Scream in the context of cloud gaming because it was not the prime service targeted by Scream. And it worked quite well on an emulated cellular traces. It was able to nicely follow the boundaries. And if we compare to GeForce Now congestion control algorithm, we can see that it's performing quite well regarding the latency. For sure, here we don't have the throughput, but regarding the latency, with the Scream CCA, we can see that most of the packets are below the 20 millisecond threshold that we consider the game is still responsive. So now we pass to the evaluation of the queuing solution, the experimental protocol. So we have the cloud gaming client and cloud gaming server. In between, we have a bottleneck. We emulate a 30 millisecond RTT between the client and the server. And the bottleneck will implement in turn either a drop tail queue, HTB, or an L4S. And the competing traffic is done by iPerf, and iPerf will use either TCP cubic or BBRv2, and we will ask iPerf to have an increasing target bitrate between 0 and 45 megabit per second, increasing the pressure on the network. And we will monitor the throughput, the queuing latency on the bottleneck, and the loss rate. So first of all, on drop tail, what we can see is the buffer bloat phenomenon. Regarding the latency, we can see because there is only one queue iPerf and the cloud gaming platform, they share the same high latency when the congestion occurs. And also the latency is fluctuating, meaning we have a high jitter, which is really hurting the QoE of cloud gaming. And also we have a very unfair cohabitation because without loss, Cubic steals the bandwidth that should be shared between the two applications. At the end, when iPerf has a high bitrate request target, we can see it follows the target, and on the other side, the cloud gaming platform as a starvation. Same drop tail scenario, but now with BBRv2, what we can see is that we are better than Cubic regarding the latency that is expecting because it is taken into account by BBR. But still we have an issue regarding the fairness because BBRv2, as you can see, the orange line on the bandwidth is taking all the bandwidth against the cloud gaming platform. So now we can see what dual queue solution can provide. First one is HTB, and we are comparing the cloud gaming platform with TCP cubic. So we can see here that the quality of service of cloud gaming is preserved. On average, we have a high throughput, and we have very low latency. And regarding the TCP flow, we have a decent throughput and much higher latency, around 1 millisecond, but because the application should not be delay sensitive, this is not an issue. And the bandwidth share is reasonable. We have 30 megabit per second for Scream, the cloud gaming platform, and 20 for Cubic. Now we are comparing Scream and BBRv2 for HTB. It's almost the same. The quality of service of the cloud gaming application is perfectly preserved, high throughput, low latency, no loss, and BBRv2 has, as we can see, lower latency than previously with Cubic, and a similar bitrate around 20 megabits per second. Finally, we evaluate the L4S architecture. First, Scream versus Cubic, and we can see that once again the quality of service of cloud gaming traffic is preserved with a high throughput, 24 megabits per second on average, and a very low latency below 0.5 milliseconds and almost no loss events. And the TCP traffic latency in the L4S architecture is much reduced, only 4.7 milliseconds on average versus 100 milliseconds with HTB. But the throughput is lower, as you can see, in average 16 megabits per second versus 19 with HTB. And another maybe point to observe is that the link utilization overall is lower with L4S than with HTB. And finally, the last experiment is Scream versus BBRv2 on L4S. Once again, very good quality of service for the cloud gaming traffic. On average, 21, almost 22 megabits per second, very low latency and almost no loss event. And we here, what is noticeable is that we have a perfectly balanced bandwidth sharing around 22 megabits per second for both flows, iPerf and the cloud gaming platform. But still, the link utilization is a bit disappointing because we are around 86-87%, while we were at more than 95% with HTB. So here we have a synthetic table of what works well and what doesn't. So on Droptail, we saw that we have the buffer bloat phenomenon. So the cloud gaming traffic had a high latency, a low throughput. And on the other side, TCP traffic has a very high throughput. And we had an unfair sharing of resources. On HTB, cloud gaming traffic was preserved with low latency, high throughput. Also on L4S, it was working very well for cloud gaming, quality of service. But we can also see a few points to observe, like the link utilization that is less with L4S than with HTB. So overall, regarding the operational advantages and constraints of both approaches, HTB advantage is that it provides a perfect isolation between traffic classes, and it doesn't need the application support regarding the CCA. But there are other constraints, like the fact that we need knowledge of the traffic to properly configure each class parameter of HTB, like the sale, the rate, the priority. And also because we need traffic classes, if you use machine learning model to identify one traffic class at the network. So we need the model to be accurate in order to avoid classification errors that could lead to neutrality violation. L4S, on the other side, has different advantages and constraints. The main advantages is that it doesn't need traffic classification, and the configuration from the ISP point of view is easier. You just have to configure the coupling factor between the low latency queue and the best effort queue. But it also has limitations. because it requires the application support to go in order for the traffic to go into the low latency queue. And still, queues are coupled, and if you have unresponsive traffic in one queue, it can steal the bandwidth. For example, we had issues with BBRV1 that was not running well on our evaluation. And yes, also dual pi square congestion marking probabilities were defined about in my DTCP and TCP cubic. And in our case, we use Scream, so maybe some parameters were less adapted to our case. So here is the conclusion. So what we have provided is a new, as a side effect, is a new experimental cloud gaming platform featuring Ericsson Scream congestion control algorithm. We have seen that cloud gaming traffic suffers from buffer bloat and with the competition with other CCA, and that both dual queue solution, HTB and L4S, can perfectly preserve the quality of service of cloud gaming platform. But they have very different operational constraints. So this study was one of the first to consider a real low latency application use case evaluated on L4S. And we have many ideas for future work, like evaluating HTB and L4S in cellular network conditions, or consider more representative computing traffic like Dash, for instance. Thank you for your attention. I'll take the question.
Nice. We have some folks in the queue, and please keep your questions brief. Rodney's first. Or maybe not. Okay, let's hear Ingemar.
Yeah, hope you can hear me.
Yeah.
Yes.
Yeah. Thanks for trying out Scream. It's really welcome that it's being used in this context. Like just one short comment, what you mentioned that you get the lower throughput and link utilization with L4S. I believe that is expected because Scream typically pays is as 50% higher than the nominal bitrate, so you lose a bit there, and then also it uses a periodic media, and you have a few milliseconds of idle time between the frames, so it's expected that you get a lower throughput or link utilization.
Okay, thank you for the information.
Christian Wittemer, have you considered doing the test with something else than L4S? I was thinking of using other AQMs like FQCodel or something like that to see whether the results do change and whether it makes a difference.
No, the idea was really to focus on L4S because it was getting popularity and we were missing a real evaluation, not based on simulation. And no FQCodel, but we could also have this in our study.
It'd be interesting because if your problem is fairness, then you might want to have an algorithm that is based on first doing fairness, and then algorithms like FQCodel, which are based on fairness, could evolve to incorporate features of L4S, and that might be something that is both as the ease of deployment that you like, and the better fairness, even when there are more than two connections.
Okay, yes, I get it. Maybe FQCodel would have been a better scenario than HTB to compare L4S to.
Yeah, thank you.
Okay,
and
Greg.
Hi, Greg White. Thank you for doing this work and presenting this. Two comments. One, Ingemar already mentioned one potential cause of the reduced link utilization in your L4S test. The other one could be a aggressive target, latency target for the classic AQM. I noticed that the classic traffic was underutilizing as well, not just the L4S traffic. So if you do repeat the experiments, I suggest trying with a higher AQM target on the classic side. And I think you'll see quite a bit better link utilization overall. Second point was on slide 21, you mentioned that classification errors could result in net neutrality violations. I think I'd remove the word errors from that point. I think classification in general could lead to a net neutrality violation. So you're dedicating some fraction of the capacity to specific applications probably is a challenging thing for ISPs to implement in a lot of jurisdictions. Thank you.
Sure, I agree. Maybe I can add that GeForce Now, so the platform from NVIDIA, knows from a few months ago, they made available an L4S option. So now you can test, if you want, L4S on a real deployed platform. So things are moving fast and it's interesting.
Certainly. Thank you again, Tibor. And
Thank you.
I'm going to share our next slides. All right, Zili, you have control now, and I'll set a timer.
Right, I have control now. So can I start?
Yes.
All right, so hello everyone, and this is Zili from the Hong Kong University of Science and Technology. So this is a draft we just recently submitted in the past week, and its aim is just like the last speaker's presentation. We are having a similar goal, but the methodology is a little bit different. We are trying to propose something that is an alternative to the L4S, but in a more deployable and a more performant way, I would say. So we call it Confucius. So the background here is basically common in basically every competing scenarios. For example, now we have the web traffic, we have the file transfer traffic, we have the video conference traffic. They are all competing for one bottleneck queue. But one thing that is different, which we notice, is that some flows or some applications, their traffic are extremely bursty. For example, on the right-hand side, this is a screenshot from the dailymail.co.uk. You can see in one web page, you have a lot of different elements. The image, advertisement, the video, the JavaScript, they are all coming from even different domains. So by nature, there are different flows. So we did a measurement. We did a measurement over the Alexa top 1,000 websites in the last year. So basically, the result is, if you take a look at the 90th percentile of all the websites, they are having almost 20 active flows running at the same time. Note that this is not something that the browser can limit. Let's say in the HTTP 1.1, you set the limit to 6 or 8 connection. They are actually coming from different domains, so different IPs. So there's no way for you to limit from the HTTP level, and that is the fact. Okay, so now assume they are competing with each other. You are loading a website, and I'm trying to using the Zoom in a video conferencing session, and they both join the bottleneck queue. Let's say it's a wired queue or wireless queue. It can be the last mile queue, or it can be any other queues. So what options do we have for now? The first and the default in Linux nowadays is fair queuing, right? FQ. No matter it's FQ Kodo or it's other, it's using the fair queuing. So what will happen is, as you can see from the down right corner, the green area is the bandwidth share by the Zoom flow. Here we denote as HRT, heavy real time. And when the web flows start to compete with the Zoom flow, all the bandwidth share will be immediately grabbed to the new web flows, right? If there are 20 flows joining the computation all at once, then the Zoom flow's available bandwidth will be reduced to 1/20 immediately, in effect. This is very bad for the congestion control, because congestion control has no idea about this sudden abrupt bandwidth adjustment, and it has no time to react either. So what will happen is, if you measure the delay for the video frames in the Zoom, you will see a huge spike at the moment where all the web flows join in the computation. This, of course, will gradually be drained, but the spike is already there. And the video flow or the Zoom flow will be severely degraded. Okay, let's assume you are using FIFO. Because you may think web flows are usually small flows, right? They are the mice flows. They may not be a long-lasting flows. Even in that case, for nowadays, the initial congestion control window is already 10 packets or even more in a lot of CDNs, which will have already incurred a huge hit to the existing Zoom flow. So you will still see a spike. Okay, then if you want to make sure that the Zoom flow is having a good experience, another way might be, what if we just enforce the strict priority, right? As you can see here, SP, strict priority. Of course, the Zoom flow will have a very stable latency all the time, but the outcome will be the web page or the web flows will have a much higher page loading time in this case, actually 1 times more than the fair QE. So none of this is perfect in this case. So let's try to see why the reason, what caused the increase in the delay of the Zoom flow or the video conferencing flows. On the right-hand side, let's say the blue line is the available bandwidth for the video conferencing or for the real-time flow. All of a sudden, it might be immediately reduced by a factor of k because of the computation, because of the new flows joining. But the center or the congestion control takes time to react to this cliff, right? Let's say the dashed green line here. It first needs a control loop. It needs to know what is happening in the network. And even if it knows what is happening in the network, it still takes some time to converge to the new sending rate. No matter you're using BBR or using Cubic or using GCC, Scream, whatever, you need some time to converge to the new sending rate. So during this period of time, all the packets being sent to the network, they're actually excessive. And they take a longer time to be drained because the bandwidth is already reduced. So this is due to the responsiveness of the congestion control algorithms. Okay, so what can we do here? So in the past decades, a lot of people are trying to, for example, predict the network bitrate or predict the available bandwidth with a more and more accurate settings. But as we all know, it does not work that well because the prediction is hard. So what we are thinking is, can we try to change the way of allocating the bandwidth across in different flows into a more gentle way? So when the 20 new flows join in the computation, instead of immediately remove all the bandwidth from the video conferencing flow to the web flows, we can gradually change this. So in this way, you can see the area here is actually bounded. And you drain more packets during the beginning of the computation. We also give the congestion control algorithm some time to react to this change. So this is the basic idea. So we actually use a deficit weighted round robin. And when the new flows join the computation, you can actually gradually increase its weight from a very low level and to 1, instead of directly setting it to 1. You can read more details in our draft submitted in the data tracker. But the idea is we can try to increase the weight of new flows gradually. So we measure the result of we call it confusions. We measure the result in the similar settings, which we will talk more about the setup later. So you can see confusions not only can make sure the delay is it's not fluctuating, basically only a small spike around the beginning, but it's roughly stable because we use a gradual adjustment of the bandwidth share. And finally, after it converges to the fair share, then we follow the previous settings of fair queuing. We still do not want to sacrifice the fairness. So here are several examples of using that. For example, in the example A here, right, when there was 1 real-time flow and there are 9 new flows joining the computation, you will see that the bandwidth share of the real-time flow is gradually reduced. instead of sharply reduced to 1/10. And this will give the congestion control some time to react. And you may ask, what if the new flows are arriving one by one, right? In the real world, probably flows are arriving one by one. Still the same. The configurator is still able to handle this scenario. Or if the flows are really short, they converge back. Or if they're new real-time flows, I will not present more details about these examples, but you can read more in our draft. So we did two set of experiments. One is we evaluated over NS3, and we load or we make a data set about over 2,000 websites, and also different bandwidth data sets in the cellular, in the Wi-Fi, in the Ethernet. We test what if the real-time flow is using COPA or using GCC, which are two typical congestion control algorithms used by the real-time applications. And we test with a set of different AQMs and bandwidth allocation mechanisms. We can see that we can always have a better trade-off, especially much lower stall duration, which is the duration of the time where the latencies exceed a certain threshold, and also maintain a roughly reasonable page loading time. We also had an implementation on the OpenWRT to modify the Linux kernel. So you can see a similar result when you are comparing the RTT and comparing the page loading time when you are trying to compete with no matter the previous class-based queues and the FIFO and fair QE. Note that one huge benefit of Confucius here is that it actually does not need any cooperation from the application. So the reason why we intentionally have this is that even if you're using L4S, you are using like in the past EC and whatever, your choice on the congestion control algorithm will be extremely limited because you need the cooperation between the sender and the router. So now here, as long as the Confucius can try to adjust the bandwidth shares in a gentle way, no matter what congestion control algorithm you're using on the sender side, it can be COPA, it can be BPR actually, it can also be GCC, whatever. We have actually an archive preprint on that. We test a lot of different algorithms. They all work. The reason here is because we are trying to make sure the real network is emulated back to the sender and they can react. And another very good feature about Confucius is that the amount of jammed traffic is actually theoretically bounded. This is because this is due to some like math knowledge. So the integral of an exponential function is actually bounded. If you integrate, let's say 2 to the power of minus x from 0 even to infinity, the area is still fixed. So this is the red shaded area here. Is the area that if you're using fair queuing, the amount of traffic that you will extensively send. And if you're using Confucius, the amount of traffic that you will get the opportunity to send more. So this is actually bounded for any time. So the loss or the penalty for the competing flow is actually bounded. And usually this can be completed in like several RTTs, 3 or 4 RTTs is already enough for congestion control algorithm to reduce its sender rate from very high level to a relatively low level. So we also have a theoretical analysis on the details, but due to the time limitation, I guess I will skip that. Basically, that is the idea for this work. And I'm wondering if you have any questions and comments or any concerns about this, and we'd like to see how the community or how the research group reacts to this proposal. Thank you.
Great. Thank you for your presentation, Zili. And we have Björn.
Yes, hello. My name is Björn. I'm from Domus. First, thank you for the work. I think this is an excellent idea. Having less sudden changes in round trips and available capacity and everything helps make congestion control an easier problem to solve. So yeah, +1 for this. It would be very interesting to see work on how the different congestion control algorithms, how their performance changes when you make this change to the bottleneck. Thank you.
Right, thank you so much. And actually, we are trying hard to make the source code available, but I think I anticipate the unnecessary simulation and the Linux kernel implementation will be available by the end of next week. I will update in the next version of the draft.
This is Stuart Shash from Apple. Is it possible for you to go to slide 8?
Slide 8. Yes.
I think this picture you have here is a little bit oversimplistic because
Yeah, sure.
your blue line instantaneously drops, whereas in the example you were giving of loading a web page, it's going to start off with some kind of slow start phase. So it doesn't immediately, that the web browser doesn't know my share of the bandwidth is X and then immediately pile on and start sending at that rate. It does the normal 1, 2, 4, 8 exploration. So the blue line, I don't think would drop instantaneously like that. It would be more of a smooth transition. And your green line of the video conference rate shows that after the control loop time, it does a smooth linear decrease until it gets to the right level. And we've known for like maybe 30 years the principle of AIMD, additive increase, multiplicative decrease, which is precisely to avoid this problem that when a sender realizes it's going too fast, it needs to make aggressive corrections to avoid the congestion collapses of the 1980s. So Reno halves the data in flight, Cubic drops it by 30%, but none that I'm aware of do a smooth linear decrease until they hit the right level.
Oh, that's a very good question. So like in the real world, of course, it's no longer linear. It can be exponential, most likely, right? So it will drop earlier in the first part and later in the second part. But that's what we are trying to emulate. That's why we use exponential function to decrease the bandwidth share instead of a linear function.
Ian Sweat, Google. I just want to thank you first for doing this work and attacking this problem. I've been complaining about this problem for many years, and I think people don't realize that something like 99% of flows on most major servers never exit startup or slow start. And so all the convergence questions that we ponder so deeply are largely irrelevant, sad to say, sorry. It's not my fault. If we had one flow, then it'd be a totally different situation. But also identifying that 20 flows is extremely common for modern browsers loading modern websites, as you did. And thank you for doing that. I did that kind of analysis of actually the top 20 as well, like 5 years ago. It was the same thing. Wikipedia, I think, had like 1 connection. Everyone else, it was at least 10. And understandably, congestion control doesn't operate well in that scheme. So I'd love to see more research in this space in general. I need to look at your specific solution a little more to evaluate it. But I mean, I just like the fact that you're really attacking the problem.
Thank you so much. And by the way, I'm also be in person from next day, from tomorrow. So if you have more questions, we can have a in-person discussion. Oh, sorry, we still have Michael here.
Yeah, let's have Michael. Please be quick.
Since you said that the delay of the web transfers, that the page load time has increased basically to double, I am curious how far away these senders were. So what is the delay between the sender and the bottleneck, or even the overall round trip time for these web flows?
Oh, you mean the experiment studies, or you mean the real world situation?
No, your experiments.
Oh, actually, we use trace. So I would say it ranges from like 20 to 30 milliseconds, but it's using different cellular and Wi-Fi traces, but it varies a lot.
Okay, but when you said that the page load time increases by 100%.
Oh, so that's the three. Like that's not that's the 3 priority. Let me here.
Yeah. Okay, but was that using a trace or was that using?
It's still using trace, but this website is actually Amazon.com.
Okay. Okay.
Because Amazon, you know, it's very complicated in this page structure, right? Just like
yes.
probably Daily Mail. If you use Google, this will much less significant as Amazon. But Amazon, this is the factor.
But did you look at the RTT of the flows?
You mean the RTT for each packet, or?
Well, in general, to the Amazon, these Amazon flows.
Oh, I would say it doesn't affect that much because they are mostly short flows. And
Okay,
after
yeah.
2 or 3 RTTs, but you think in this way. So page loading time, no matter high or low it is still at second level, right? 1 or 2 seconds. So this granularity. At this magnitude, it's already 20 to 30 RTTs, or even more.
Okay, yeah.
We only need the first 3 or 4 RTTs to smooth the adjustment period. We do not need like the whole 1 second to adjust this.
Yeah, I agree about that for your mechanism. I
So
was just
after
curious
after
about
the first transition period, RTT will be stabilized as the
yeah.
past.
No, I agree with that. I was just curious. So,
Thank you so
thank
much.
you.
Let's follow up offline. Thank you, Zuli, and hope you will be able to join in person. And then next we will have Costin. If you wanted to screen share, I'm also happy to just load your PDF slides. That's what I was intending to do. I think you're in the room, right? Oh yeah. And you have. Okay.
Oh, it's only going to upload the PDF. I'll have to like click my.
If you want to click, you can do the PDF.
No, no, no. The problem with the PDF is that it doesn't have my animations properly. Hi everyone.
Your slides are not yet up.
Let's see what's happening. I do hope the timer is not right, because I prepared this for the original 45 minutes. Anyway. All right, so this is a completely different application domain. So all of these previous talks and the scope of the IETF is for the internet. This is about data centers and a very particular type of data center, as in data center network, which is the ones that people are building now in massive scales to support AI/ML training and inference. So this is, all the rage in sort of the hyperscalers and even the sort of second tier enterprises, and there's a lot of activity around this. Yeah. Well, in that case, it's a bit. Well, it's disappointing that the other talks went over them. Anyway, all right. So tons of money being piled into this, and basically, what people are building is really large data centers. So OpenAI, public plans, they're going to build like a 5 gigawatt data center that they want to use to train like big model at the same time. All of this needs to sort of act like a single computer. Okay. So if you actually look at the power you have, you kind of figure out that you cannot have it in one place. There's just not enough power in the US for this, right? So most likely they're going to split in two parts. It makes most sense to split, for instance, East and West Coast. So that means you'll have to have like really high density data centers in these networks in these two data centers, and then somehow make them work across the wide area. What I'm going to talk about today is mostly what you do in a single data center. If you're curious about wide area, then there's a paper I can point you to. Okay, so if you build this data center, you have clearly a big model in mind, and these are the scaling laws that basically say how big the model should be given the compute power you have, and basically what we went. So this is a paper we published last year in HotNet. So what we went for is something really big, which is like 50 times larger than what people trained so far. So if you go for this really large model, you can kind of fit it in this humongous data center that OpenAI are building. And the question is, well, how do you train it? Well, networking, from a networking point of view, these clusters are very sort of specific. Like they differ from the cloud networks because you have these thing called nodes. And within a node, you have many GPUs, right? And the current scale of a node is typically 1 rack. So in the current packaging that NVIDIA is proposing and others are following suit, you have 72 GPUs, and each of these will have a NIC connecting to, let's say, the data center or the scale out network. but they're also connected to a scale-up network, which is a rack-only network, which is much higher bandwidth. So, this is sort of the NVLink and the switch domain, and the scale-out network is your traditional sort of data center network, right? But again, these are dedicated networks. They're not the front-end network that people use to sort of serve the normal TCP and other traffic, okay? Okay, so if you want to do this model, then what you have to do is sort of place it, spread the model across the many GPUs you have. And for instance, if you look at the number of layers you have and you figure out the memory constraints, you see that you can have a single layer requires a quarter of a GPU just to sort of store the model, right? A quarter of a node, sorry. So, quarter of a rack. So basically, you will have 4 replicas of your layer within a rack. And it makes most sense to have the same layer. So in this case, we'll have like layer 1 here. And then, of course, you'll have to have many racks to hold all of your layers, which is in the order of hundreds, and then communicate across racks as you're training, right? That's the idea. So, and of course, you're going to have many replicas of these. So, hundreds of replicas. Okay, so how does the training work? So you've got your, crawled internet, right? Stored somewhere and crawled everything else. And, then you basically break it up into batches and you put it in this model, right? So, and here it's going to go in the first layer, right? And the first layer, obviously these are many GPUs, so there's some compute happening, and then this sort of magenta thing says this is some communication across the local scale-up network. Once this layer is done, then this sort of reddish thing says you communicate across wide area network, sorry, the data center network. So you go out to the scale-out network, and this is called pipeline parallelism. So you go from layer 1 to layer 2, and then you go all the way to the last layer. You have some output that is probably wrong. You compare it to what you really want, and you do this thing called backpropagation. And again, you have scale up and scale out networking, and this all comes back. And of course, on the backpropagation phase, what you need to do is to synchronize all the replicas you have that are independent, right? So you've created many replicas of your model. You're putting different data into those replicas. But if you don't want them to be out of sync and turn into separate models, you have to like synchronize them on the way back. And this is this all reduced thing that you have to do. And actually, this is a lot of data that you need to sort of move across. Okay. So just some basic numbers. We estimate that it's going to take around 400 milliseconds of compute for both forward and backward pass. And most of the networking can be hidden behind this compute, but some of it cannot. And this is called exposed networking. And the main goal when you're building these networks is to minimize exposed networking. That's the goal. Okay. So depending on the model you have for your transformer, it can be more or less. I'm not going to go into details because I don't have that much time. Okay. So, yeah. It sort of includes everything, right? There's going to be a lot of hierarchical. So I'm not sure how you want to do this. I mean, I'm happy to take questions. The thing is, I'm going to go to like a quarter of my slides, and I've flown like 15 hours for this talk. So I'm not sure. It's, yeah. Anyway, so, okay. So how big does your network have to be in terms of per node throughput? Okay. So this is the scale up speed, right? So the NVIDIA proposed point is this one, okay? What I'm showing on the y-axis is what fraction of your networking is exposed, as in makes the GPUs go idle, right? So lower is better. Ideally, you want 0, okay? Now, obviously, 14.4 is pretty good, but if you go lower, you're gonna have more exposed networking, which is pretty bad. And if you don't have any scale up, if you don't have any scale up, it's really, really bad. So basically, this means that these rack networks are really important, right? So you have like 2 networks to serve 1 workload. And then for the scale out network, what is the throughput you need per node? The current point is 800 gig here. Depending on your architecture, this may be good enough, or you may need even more, okay? So if you look at the speeds, you'll sort of notice that if you put an 800 gig NIC into a CPU box, you'll have a really hard time filling it in. with these GPU things, it's actually very easy to saturate 800 gig, which is sort of surprising. Okay. All right. So this is the capacity we want. How do you build a network, right? So we're going to focus on scale out. Scale up is a completely different sort of discussion. I don't have time for that. Happy to chat to you afterwards about that. Okay, so these are your racks, and somehow you have to connect them. So the standard thing is to just do a multi-tier close, like people are building in hyperscalers. There's a lot of experience in building these for front-end networks. Why not do the same? Well, the answer is it's actually very expensive, and the reason is, well, the maximum number of nodes you can support is basically the number of ports you have in a switch, the switch radix, to the number of tiers you have, right? So there's a sort of a power there. And if you want to do 800K nodes, which is our target, you'll basically need 4 tiers, okay? And the problem is that when you're connecting, so every single tier you have, you're basically adding a lot of capacity that is proportional to the number of GPUs you have, because I also didn't mention that a lot of these networks are fully provisioned, right? So you have to have the same capacity at all the layers, more or less, and then that basically, you buy a lot of switches for this. And the problem is, not only you have a lot of switches, but you also need a lot of wires. And the wires are really expensive because they're optics and they require these sort of active optics and retimers. So the cost of the wires is billions if you do this. Okay. So then you have to cut the cost somehow without cutting the actual bandwidth available per GPU. So what you can do is you can observe that some GPUs talk in pairs and they don't talk to anybody else. So for instance, if you take the first GPU from every single rack, typically they talk to each other, right? Because they hold sort of the same part of the model, layer 1, layer 2, whatever. So you can do this thing called the rail that only connects these GPUs, and it's basically 1/72 of the nodes. And then you'll have 72 rails, and these are independent networks. So a blue node cannot talk directly to a yellow node via the scale-out network. They'll have to go via the scale-up network, either the source store or the destination store. So all of a sudden, this becomes sort of an interesting communication pattern if you want to go across rails. Okay, and this actually helps a lot because it allows you to reduce the number of tiers by 1. So you only have 3 tiers now for our target data center. And the other thing you can do, becomes even more interesting, is that with the current capacity switches that we have, like 51T switches, you can configure them as 64 times 800 gig ports, or you can configure them, for instance, as 256 200 gig ports, okay? So if you do the latter, then what you can do is you can take 4 switching chips and basically place them in the same box, right? So you have 4 ASICs, you place them in the same box. They act like 4 independent switches, but you have a single wire to connect to this big switch, and inside the switch, you have copper backplanes to the different ASICs. So it's like you're deploying 4 parallel 200 gig networks with much higher switch radix, and you're using 1 wire for each link, right? And this basically gives you, another reduction in the number of tiers, right? This is nice, but now you don't have 800 gig per connection. If you want to have an 800 gig connection between these things, you must stripe across these 4 planes. Otherwise, well, it's not going to work. Okay, so these are how people are building these networks. They're using all of these tricks to reduce the cost, and typically the networks will be either 2 tiers or 3 tiers, not more. Okay. Now I'll just skip this. So this is pipeline parallelism, is going from one layer to the other. Typically, what you do is you do a lot of sharding and use scale-up communication to minimize how much you send over the scale-out, and this will take, for instance, 2 milliseconds to do just one pipeline operation. The interesting thing is everybody's sending at the same time to somebody else, right? And they start at the same time, they finish at the same time, and they fully load the network. That's basically what's happening. And if you look at this hierarchical reduce, again, this is very interesting how it's done. You basically break it up into some scale-up communication, and you shard the data that goes across the long distance to basically make sure that everything finishes as quickly as possible. And actually, again, I don't have time to go to the slides properly, but The idea is if you look at the scale out network, traffic will start at the same time across all the GPUs in a rack. They will go across the scale out network. Some of it will go across the wide area, but let's focus on the scale out. They'll go across the scale out and they fully load the scale out network, right? Everybody talks at the same time, right? And this is important. Okay. And if you do all of this, then you're within the budget you have for your GPU compute, and you can sort of hide the networking behind the compute. If you don't do this properly, then all of a sudden the network is slow, the GPUs go idle, and your training time will take like 10 times longer or something, and everybody's unhappy. You've paid a ton of money for your GPUs, and it's bad. Okay. So, all right. So now let's talk about the networking part. So this was more about the workload. So the workload is a lot of parallel flows trying to go through the core of the network. They are not very long, just a few tens of RTTs maybe. They all have to finish at the same time. Okay. How do you do the routing in a flow? Probably people know about this. So, there's a lot of paths between any source and destination, and ECMP hashes the 5 tuple in a flow to decide which of the paths available it should take, right? So basically, if you have this flow going like this, and you have this other flow going like this, they may collide because ECMP, is random and doesn't have any sort of network state. So you can get collisions that will actually result in a lot of wasted throughput. And this is what we have today. So today we have single path flows that are either Rocky or InfiniBand. The network is the industry is moving towards Rocky and Ethernet. So Ethernet is, has already won this battle. It used to be that people trained over InfiniBand. That didn't scale. It's single source, a lot of problems with it. People are moving to Ethernet. All the hyperscalers now have either already deployed or are deploying Ethernet. So basically, you're going to have something like Rocky going over this. And then the question is, well, how does the Rocky flow, how long does it take to do pipeline parallelism with Rocky, right? And what I'm showing here is an 8K network with 800 gig links and the same flow sizes that I was showing earlier. And the network is provisioned to have like 1 millisecond flow completion time, but with Rocky, what you see is more like 9 millisecond flow completion time just because of collisions. Okay, and this is sort of something that people know. The question is, obviously, Rocky has PFC and has all of these issues. So the question is it just because of Rocky? If you have a good congestion controller, can we get much better performance? And the answer is, well, not really. If you take a sort of state-of-the-art congestion controller and you apply it, you still have like 7 millisecond FCT. Okay, so okay, so what do we need to do? Well, we really need to go to multipath, right? So if you go to multipath, then if you have 2 paths that you use, you get something like 3.5 milliseconds, 2 paths for every single flow. Yeah, if you use 8 paths, you get just under 2 milliseconds. Finally, if you go to something like 128 paths, you cannot really see it, but you're basically just 10% worse than the optimal, right? You're within 10%. So this says, well, you really need multipath for this thing to work. And this is where we're going. The industry has already sort of embraced the need for multipath in these AI/ML networks, and there's standardization work in sort of defining the next Rocky that will have this. Okay. Okay, I'm gonna skip this slide. All right, so let's try to see what we need for a AI/ML transport. By the way, a lot of this stuff is already close to standard level. There's this thing called the Ultra Ethernet Consortium that has been working in the past 3 years on defining this. And the specs are not public yet. They're going to be available in basically this spring. So a lot of the things here is stuff that I'm allowed to talk about and stuff that is already public. But yeah, if you're curious about the final, like the full details, you're going to be able to see them in a couple of months. Okay. So the requirements are very clear. You want to be able to spread the traffic across available paths. You have short flows. You need to be able to start at line rate. And the problem is that switch buffers are not really scaling with the link speed, so there's a problem with buffer pressure, right? If you start at line rate and you have some sort of collision at the receiver, what do you do? Okay, so some people know me because I spent a lot of years here optimizing multipath TCP. Well, this looks like a great solution for this problem, right? So you basically have subflows, and each subflow can take a different path, and then it's all great. And multipath congestion control sort of shifts traffic around to move it to the least congested path. So it's all exactly what we need. Except it's not really, right? So it's pretty good, but there's something missing. So the first problem is that it actually takes sort of 2 RTTs to have subflows set up in a multipath TCP connection. That's actually very slow. Let's say we could fix that. Not a big deal. The other problem is that the load balancing that MPTCP does actually works really well for long flows. It doesn't work very well for short flows, right? And MPTCP typically uses 8 to 16 subflows, right? And there's a reason for that. If you try to use many subflows like 128 or 256, like people are saying for these networks, there's a huge problem. The problem is we have a minimum window, congestion window per subflow of 1. So if you take the aggregate window across all of these subflows, you're looking at 128 packets to 256 packets, okay? That's actually too large. That's the BDP in these networks. So you'll congestion collapse if you don't do anything else. So that means if you want to do MPTCP, we'll have to do some sort of sub-packet windows for subflows, which is very complicated. And if you take all of these together, it's very complicated to implement in hardware. It's going to be a lot of area to be able to support this. So people are looking at simpler solutions. And the idea is, well, let's do packet spraying. Packet spraying, there's this idea that, well, we have, hold on, we have a single window, a single congestion window that says how much we can inject. We don't keep per path congestion windows or per path sequence numbers or anything else. It's a single window, okay? However, within the single window, you still put packets on different paths. It's just that that's sort of an independent process. You're not tracking per path windows, right? And given that we're in a data center and this is very well-known deployment setup, we basically limit this total window to just 1.5 BDPs. The BDP is known, so we can basically say you should never go more than this. And actually, we start with 0 RTT setup and we start at line rate, okay? And then spraying basically says, when I'm sending a packet, I will put some entropy in it. An entropy value is the term we use. And the entropy could be the UDP source port or some other packet that the switch is hash. And I will basically vary this value such that probabilistically my packets take different paths, okay? So this is the idea. And of course, the question is, how do you choose these EVs? Okay, so packet spraying, basically you change the entropy and then it looks something like this. So basically it's gonna go across all of the available paths. You could still have some sort of short-lived collision. So this may not be completely perfect, but it's gonna be obviously a lot better than single path. But you're gonna get a lot of reordering. So the question is, how do you do reordering? Okay, so you start at line rate, as I said. The problem is when you have a bunch of flows starting at line rate and they're all going to the same destination, you're gonna have a lot of problems towards destination. Those buffers are gonna get full, things are gonna go pear-shaped. So you're gonna get this problem called incast. So the question is, what do you do about incast? One option is to pause flows with PFC. This has so many issues, I'm not gonna even talk about it. But the biggest issue is basically when you get a single congestion point, this thing pushes congestion throughout the entire network, stopping traffic that is really not going to the same destination. And if you want an analogy, this is like using the same thing you have on car networks, on roads, and applying it to networks. It's like a really bad idea. Okay, so obviously you don't want this, you want something else. We could just have normal loss, but then detecting loss is very hard. So what we're doing is this thing called packet trimming. This is something that we proposed in research, I think in 2018, and other people proposed it earlier. But the idea is this: for every single port, you have two queues, right? You have the regular data sort of buffer, and then you have a higher priority buffer that you can use. And you dimension these things very aggressively. So you basically have 1 BDP of data, okay? And now when the red packet comes in and it cannot fit this buffer, instead of just dropping it, you basically just drop the payload of this buffer, just keep the header, the transport header, switch the DSCP code point on it, and it goes into this higher priority queue, and this goes to the destination. And this tells the receiver, your packet was lost. It tells it the packet was lost, and then also the receiver can generate a NAC quickly to the sender saying, you need to retransmit this packet. And then, you need to slow down because things are bad. Okay, so that's the idea. Trimming is already a standard. So it might be that I can even share this with you because it's already past sort of the working group last call and everything. But the idea is that it's a standard and there's multiple vendors already supporting it. So if you're doing congestion control for data centers, you need to assume that this is available, right? And of course, data centers are one hop in the internet end-to-end path. So you could use streaming for internet if we can find a way to make it work from a congestion control point of view. Not sure you can, but anyway, this is something that the switches give you. Current generation, next generation switches are going to have this. It's a standard. There's a question of when this gets brought into the IETF and how. That's a question we'll have to figure out, but it's going to have to come in. Okay. All right. So congestion control. Again, there's two options we could do. We could do like normal sender-based congestion control, or we could do something at the receiver. I don't think I have time to talk about this, so I'll just skip it. But the idea is if you do the trimming and the line race start, even something like DCTCP would work. So it's not a big deal. Basically, to improve performance beyond DCTCP, you can do it, but you're going to get some gains. They're not going to be absolutely amazing, right? So and then you can basically, if your network is fully provisioned, then you can do this receiver-driven control where the receiver gives out credits to the senders, and this works really well if you have a lot of incast. It works like perfectly. So okay, let me just skip this. Okay, so congestion control mostly skipped. I think it's interesting to sort of discuss how does the packet spraying work, right? With MPTCP, you had this per path congestion window that was sort of seeing if a path is bad, you pull traffic away from it. The question is, what is the equivalent in the spraying world? And the simplest thing you can do is this thing called oblivious. Oblivious means I just pick a random source port for every single packet, and I really don't care. And this works actually pretty well if capacity is uniform. Let's see, okay. So in this particular example, the optimal FCT is around 180 microseconds. The flows, they're all starting at the same time. This is like the equivalent of pipeline parallelism. And if you had like a perfect schedule, it would be like a 180 straight line. If you do oblivious packet spraying, but you allow the buffers to be something like 10 BDPs, this is what you get, right? So the tail there is because you still get some imbalance. However, if you have a 1 BDP buffer and you trim with 1 BDP, this is what you get. You get this blue line, right? Basically, if you get the ECMP collisions and some buffer is growing, what's going to happen is that you're going to get the trim. The trim goes to the receiver, goes back to the sender retransmits, and then it probabilistically picks a better path, right? And this way of load balancing actually works pretty well. So you get this, you're around like 220 microseconds, whatever that is, okay? So that's one thing you can do. Oblivious is actually pretty good. This shows, how many values do you use for oblivious. So we did a lot of simulations. What is showing here is, x-axis is number of nodes, y-axis is the load of this pipeline parallelism, and z-axis is how far off you are from optimal. So if you look at like this guy here, basically, ECMP with 64 EVs or more, you see that even for large node, you're within 15% of optimal. So this is actually pretty good. Okay. The other approach to load balancing is to keep a little bit of path state, right? MPTCP kept a lot of path state. Oblivious keeps none, just random and trim. If you keep a little bit of path state, you might be able to do better. So the simplest idea is, let's say you have 1 bit of path state. If you get an ECN mark for a particular path, you just set the bit to 1. And when you're about to use that path, you just skip it for this round and you set it to 0, right? So this allows you to a little bit load balance around bad paths. And actually, it works pretty well. And there's this other idea from the Microsoft folks that basically say, well, when we get ACKs back, if the entropy for that ACK says there was no congestion, then I have a local cache and I'll save it in the cache. If it says it had congestion, as in it's ECN marked, I'm not going to save it in the cache. And then when I'm trying to transmit a packet, I just take 1 entropy from the cache, I remove it, and I put it in the packet. So initially, you start with, by the way, if the cache is empty, I take a random entropy. So basically,
Okay,
this
Costin,
is...
we're going to have to wrap up in a little bit.
Okay, so anyway, this basically shows that if you keep some state, you're better than oblivious. And I'm going to just skip to the end. Okay. Yeah, so that was my attempt at doing a 45-minute talk into 20 minutes. Sorry,
it's a good
about
speed
that.
run.
Okay, thank you, Costin, and I'm sorry we ran out of time. It appears our Q&A sessions ran a bit over, but I hope everybody will get a chance to catch up with you over lunch or during the week. Thanks,
Can we
everybody, for the great
have
questions.
Costin come back and talk more about this, because it's really interesting and it's unfortunate that it went so short.
Yeah.
Got quite a
Agreed.
few thumbs up in the rooms for that proposal.
All right, very good.
Yeah, there's still a couple of spaces open in the side meeting signups for this week, so that might be a place to do that.
I'm leaving tomorrow, so it's going to have to be today. Yeah,
That'd be a great idea. So yeah, so especially if there are folks who want to discuss, just grab a pile and lead the train out of the room towards some food, and just keep going with more things in people's mouths.
Yeah.
All right, thanks, everybody.